Cuernavaca, dentro del programa topológica de gérmenes de conjuntos.
Muchas gracias por la invitación. Puedo hablar un poco en español, pero no es suficiente para hacer la plática en español, entonces. So, I will talk about the problem the general problem is the following. How far is an analytic set from an algebraic set? So, an analytic set is a set defined as the zero locus of analytic function, and an algebraic set is the set defined as the zero locus of polynomial functions in several variables in general. And we can look at basic examples, like you take an analytic function in one variable, like this one. Take sinus of 1 over x. So this function, which is defined for x, let's say in the unit disk, the open unique disk. And this function has an infinite number of zeros in the complex unique disk. And therefore, it cannot be, there is no bijection between the zero locus, denote this by phi. So phi minus 1 is infinite. And so it's not in bijection with the zero locus of one polynomial. But, so therefore we'll look at the problem locally. Locally means we will talk about germs. So a germ, I can speak about germ of sets or germs of functions. For sets, if I have let's say two sets, V and W, and so, sorry, I will speak about analytic functions and analytic set defined either over the real numbers or the complex numbers. So from now on, K will denote R or C. And there will be essentially no difference except in a particular case where I will. So I take two sets in Kn. I pick a point in Kn, I will take the origin for simplicity. And that belongs to both sets. And I will define an equivalent relation of such a set by saying that V and W are equivalent if there exists a neighborhood of 0, denoted by, I don't know, U, such that V intersected with U is equal to W intersected with U. So the sets may be different, but locally they're the same. And such an equivalent class is called a germ of sets. And if I consider analytic set or algebraic set, I will speak about germs of algebraic. And I can define germs of function in the same way. I take two sets, like before, V and W, containing the origin, and I pick two functions, V, one divided by f from V to k, and g from W to k. And I say that these functions are equivalent if there exists, as before, a neighborhood of the origin of 0, such that f restricted to u is equal to g restricted to u. As before, the function cannot be the same, but locally they're the same. Okay? And such an equivalent class is a germ of function. And because I'm speaking about analytic function, there will be f and g will be analytic functions, so I will speak about germs of analytic functions. And in fact, germs of analytic functions define in the neighborhood of the origin in Kn are isomorphic as rings, because they're rings, the set of convergent power series. Because I can identify such a germ of function, which is Taylor expansion, and this identification is a morphism of ring, and it's an isomorphism, in fact. Convergent power series, and the ring of convergent power series will be denoted like this. Okay? So, the question now is, locally, how far is an analytic set from an algebraic set? And I can be more precise. First question is, given a germ of an analytic set, can I find a germ of isomorphism that sends this analytic set to an algebraic set? So given V0, a germ in Kn0, a germ of an analytic set. Okay. Does there exist H, an isomorphism from Kn into itself, such that H of V0 is algebraic? So defined by polynomials. Here I denote V0 to say that it's a germ at 0. And the map is a germ of isomorphism, means that 0 is sent over 0. So that's the question for sets. And I can ask the same for functions. So given the function like before, germ of function, f from V0, or for k, let's say Kn 0 to k, germ, an analytic germ. Same question. Can I find a germ of isomorphism from K into itself that composed with F give a polynomial function? So that's the goal of the talk, it's to give answers to this question. We can think about this germ of isomorphism as change of variables. So the question can be rephrased in, after some change of variables, is my set given by, is the zero set of some polynomial function, or here, given a series, because series, convergent series are the same as germ of functions, given a convergent power series, can I find a change of variables that transform my series into a polynomial? So, I will give examples. I will consider the case n equal to 1, first in the beginning. And I will look at question 2. So I have a germ of analytic function from k to k. And in fact, f, so f of x is one variable, is just a series. And such a series in one variable can be written as a monomial, x to the d, times u of x, where u of 0, is different from 0. So I can always factor out the largest monomial dividing all the monomials of the series f, and I write it like this. Okay? And because u of 0 is non-zero, I can consider the root of u of x, or in the real case, plus or minus the root. So let's say here, k is C. And this is an analytic function also, so it's given by a convergent power series. So f of x, I denote this by v of x. And so f of x is, in fact, x times v of x power d. Sorry, not the root square, the d root. Like, okay? And v of 0 is different from 0, because v of 0 is different from 0. And the map, let's say h, from k to k, which is in fact a map, germ of map, because it's defined locally, because this root is just defined locally. That sent x over x v of x. Its derivative at 0 is different from 0. It's just v of 0, in fact. And so it's a local diffeomorphism, analytic diffeomorphism. And so the inverse will give you the following. If I compose f with the inverse of h, you will obtain exactly x to the power d. Okay? And if I work over the real case, I will have here to replace u maybe by minus u, and so I have maybe a minus there, and I will transform my series into minus x to the d. So in any case, in the case n equal 1, we can answer the second question easily, and the first one also, because it's just a finite number of points. It's essentially the same way of doing this. Oh, there are 3 blackboards. So one more example, the smooth case. So I will also look at this question 2 because it's a bit more easier to handle. I assume that let f, so a series. So from now on, x will denote a tuple of n variables like this. C or so k, maybe the real. And I assume that f is smooth at the origin, so I mean that one of the partial derivative of f, one of the partial derivative of f, at 0 is non-zero. Okay? And let's say, for instance, that it's the first one, for simplicity. Now I consider the map from kn 0 to kn that sends the point x1, xn over f of x, x2 up to xn. Because this derivative is non-zero, this map is an analytic diffeomorphism. Diffeomorphism. So h minus 1 is well defined. And if I look at f composed with h minus 1 of x, I will exactly obtain x1. So once again, in this case, we can transform easily a convergent power series into just one monomial, one variable, in fact. So these are the main basic examples. And for sets, it's the same. If a set is smooth, it means that locally at 0, it's a manifold. Then we can also transform this manifold into a hyperplane, linear hyperplane, by a local analytic diffeomorphism. Actually, the same. Okay. One more case, which is not that easy, and I will not give a proof of this, but it's the case, the isolated singularity case. So for instance, for functions, because I begin with function, we consider a function f like this. Such that the common zero locus of f and its partial derivative is the origin. So such that f of x equal x1. So if this system of equation has only one solution, which is locally the origin. Which is 0. So the previous case, the smooth case, is the case where this set of equation has no solution. And the next case is the case where the solution is an isolated point. So in this case, we can always, let's say, question 2 has a positive answer. So it's not that trivial. In fact, the first partial result, it was not that general, is due to Samuel in 1966. And the general case has been done by Kuhash. I don't know. Mid-80s. So it took 30 years to prove this. And the proof is very easy in some sense. It's just a very clever use of the implicit function theorem, but it's a bit tricky. In this case, also, question 1 has a positive answer. So, still we also have Q1 as a positive answer if V is an isolated singularity. I mean that locally, all the points of V, locally at any point different from the origin, the V is a smooth manifold, except maybe at the origin. This can be written also as some vanishing of the differential of the equation defined in V, but we can say. Okay, and the proof is more or less the same for question 1 and question 2. So the next case is the case where the singular locus is not smooth. It's not a point, sorry. So I will present an example due to Whitney, 69. So this is the zero set of one function in variables. So it's a surface in K3. So here, for simplicity, I will take K equal R. But we can handle the next example also in the complex case. So I consider f of, I will choose x, y, and z for simplicity. I have 3 variables, and this is defined as follows. It's x times y times x minus y, x minus zy, x minus exponential zy. Okay, so it's the product of 5 terms, I'm sure easy in some sense. And if I look, I denote by V the zero locus of f, locally around the origin. So I have 5 terms here. So if f is equal to 0, it means that one of these 5 terms is 0. So V is the union of 5 surfaces, each of them defined by one of these 5 terms. And these surfaces are smooth. They're locally manifold. We'll try to make a picture. So I have the z-axis, and the way of thinking this example is to look at V as 5 lines which are moving along the z-axis. Yeah, if I fix some value for z, I obtain 5 lines. So there are three of them do not change. And the slope of the last 2 lines will change with z. Okay? And it's a surface like this. Okay? So what is important here is that these 5 surfaces, which are smooth, intersect transversely along this axis. And so this will give a kind of negative answer to this question. So I will suppose that I can transform V into an algebraic set by some holomorphic map, analytic map, B holomorphism. I'm the real case, so B analytic map. So assume that there exists H from K3 to K3, which is B analytic. So assume so we assume that there exists H from K3 into itself, such that H of V by W is algebraic. So defined as the zero locus of polynomial of one polynomial function. So I will pick a point here along this axis close to the origin, so of the form 0, 0, z. And because the H is B analytic, so it's my assumption, I can look at the differential of H locally at some point, like this. So the differential of H at this point define a linear isomorphism from the tangent space of V W like this. This is a linear isomorphism. So what's the tangent space of V at some point of the z-axis? It's not very difficult to see that it's 5 planes. That 5 planes that intersect along an axis like this. And I can define the cross ratio of these 5 planes. So these are 5 planes. Or, sorry, if I pick 4 of these planes, I can consider the cross ratio of these 4 planes. Okay, it's defined as the cross ratio. So I have 5 planes intersecting along a line. I can take a transversal plane. The intersection will be lines, and the cross ratio of these lines does not depend on the plane we choose to intersect all this. Okay? So I can pick, for instance, the cross ratio of the first 4 planes. So one of this cross ratio will be Z, if I choose well the order of the planes. And I can choose the cross ratio, the 3 first lines with the last one, and the cross ratio will be exponential of Z. Okay? And because the map is a linear isomorphism, the cross ratio is preserved. Okay? In particular, these 2 cross ratio will be preserved, and what is important here is that Z and exponential Z are algebraically independent. There is no algebraic relation between them because the exponential is transcendental. Okay? And now W, the tangent planes, will be also 5 planes. It's the same because they're isomorphic. And I can consider also the cross ratio of these planes, but because W is defined by a polynomial function, this cross ratio will depend algebraically of some parameter, and in particular, the image of these two cross ratio has to be algebraically dependent. It cannot be independent algebraically. Because here, W is algebraic, so all the data from W will be computed in terms of algebraic functions. And so here we see that this situation is not possible. We cannot have two functions here which are algebraically independent and sent over algebraically dependent functions. So such a H cannot exist. So there is no B-analytic map sending V over W, where W is an algebraic set. Okay? So I said that I choose here K equal to R, but we can do exactly the same for the complex number. What is different in the real case is that what we really use here is that H induces an isomorphism between the tangent space. So if we weaken the assumption on H of not being B-analytic but only a C1 diffeomorphism, such a H does not exist, even in this case, does not exist. I mean, we cannot transform V, in this case, into an algebraic set by a C1 diffeomorphism, because the C1 diffeomorphism induces also an isomorphism like this between the tangent space. Okay? So there is no exist H, a germ C1 diffeomorphism, sending H, a V, sorry, onto an algebraic space, algebraic set. And here is directly the next example after the isolated case. Here the singular locus is just the z-axis, which is one dimensional, which is smooth. I mean, there is no really the next step. Okay.
But here, topologically, there's no problem. You can.
Yes. Exactly. That's the point. So, indeed, as you say, topologically, we can transform V into an algebraic set. And in fact, this is a general fact. That's a result of Mostovsky. So we have the following theorem due to Mostovsky. I think it's 84. Let's say exactly that question 1 has a positive answer if H is with H, let's say H a germ of homeomorphism. So it means that we can transform a germ of analytic set into a germ of algebraic set by a germ of homeomorphism, but not diffeomorphism. Okay. Okay. So I will give few very basic indication of the proof of such a result. To transform an algebraic set, an analytic set, sorry, V into an algebraic set, the idea will be to deform V in a continuous way. So before explaining this, I will introduce a new class of functions, which are in between the algebraic function and the analytic functions. So these are called the Nash functions. Or, because I'm working, in fact, with power series, I will speak about Nash series. So what is a Nash series? It's a convergent power series, which is algebraic over the polynomial. So definition, f in k of x, where x here denotes x1 up to xn, is Nash if f of x is algebraic over the polynomials. So it means that it satisfies a polynomial relation with polynomial coefficients. Example. You consider the Taylor expansion of the root of 1 plus x, that whose value is 1 at 0, for instance. Okay, this is an analytic function, not a polynomial function. It's locally an analytic function, and it's Nash. Okay, if I denote this by f, just because f of x squared minus 1 plus x is equal to 0. So it's a solution of the equation t squared minus 1 plus x equal to 0. Okay? So these are the Nash functions, or Nash series. And the set of Nash series is a ring. And what is important is that this ring satisfies the implicit function theorem. And even more, it's the smallest ring contained in the polynomials that is stable under the implicit function theorem. Such a ring is called Henselian ring. Okay, these are the algebraic properties of this series, but we can look at geometric properties of this series, and we can look at one, I think, basic example, but important example. We pick an elliptic curve, like this in the plane, defined by an equation of the form y squared minus, so I have a double point, let's say at the origin, x squared 1 plus x equal to 0. Okay. So this curve, algebraically, it's irreducible. I mean, the zero set of this curve, I denote this by v, cannot be written as the union of two proper curves in v. Cannot reduce as the union of two smallest algebraic sets. But now, if I look locally around the origin, so I pick, here it's the origin, I pick a small neighborhood of the origin, and so I don't know what happens away from this, so I erase everything. I see two lines crossing like this. And these two lines give you a set which is reducible. It's the union of two different subsets, analytic subsets. So here we have a curve which is algebraically, which is irreducible, but locally, if you look as an analytic set, it's reducible. And you can see here, in fact, this polynomial is irreducible because this function is not square. It's not a square of one polynomial, but this is the square of one Nash function, Nash series. Because in fact, y squared minus x2 1 plus x can be written as this, this. Okay? And so the zero locus of this polynomial, locally at the origin, is the zero locus of this function, union the zero locus of this function. And it's a general fact. What I mean by general fact, I mean that Nash functions, or Nash series, or Nash set, yeah, I can define also Nash sets. there are analytic sets defined as the zero locus of Nash series. So a Nash set is defined as the zero locus of Nash series. And in general, a Nash set is just a union or finite union of branches of algebraic set. So what is a branch of an algebraic set or an analytic set? I have an analytic set which has several irreducible components, and these irreducible components are called the branches of the analytic set. So if I pick an algebraic set, I can look at it as an analytic set. I look at its branches, and these branches are Nash sets. It's exactly the previous example. And every Nash set is a union of such branches of algebraic sets. So, the proof, I will say a few words, but not too much, about the proof of the result of Mostovsky. Is to construct first step. So the first step is to deform V into a Nash set, a germ of Nash set. And deformation in a way that the deformation is topologically trivial. And the second step is to transform this Nash set into an algebraic set. So the second step is not that difficult. It's well known. It's a trick due to Artin and Mazur. This step is more complicated. So there are different ways of deforming analytic sets in a topological trivial way. And this is done by the so-called equisingular deformation. So the first step will involve equisingular deformation. So roughly speaking, an equisingular deformation of a germ of analytic set is a deformation of this germ into a family, an analytic family, which is topologically trivial. But in practice, we need conditions to ensure the topological triviality. And so there are different notions of deformations which ensure the local triviality, topological triviality. So these deformations are usually called, there is the notion of Whitney deformation, or Whitney equisingularity. Zariski equisingularity. There are some Lipschitz also. There are different types of equisingularities. So in fact, there are definition of some deformation which satisfy some properties that ensure the topological triviality. So Whitney equisingularity is definition in terms of differential geometry. The Zariski equisingularity is defined, it's an algebraic definition. Lipschitz geometry is defined in terms of Lipschitz conditions. And there's some variation of them. And so here in the proof of Mostovsky, in fact, he uses the Zariski equisingularity. So he takes V, and he constructs a Zariski deformation of V, which will be topologically trivial, because Zariski deformations are topologically trivial. And for this, he says that, in fact, just V is equisingular over one point, which is you don't know the definition, but it's really trivial. A set is always, an analytic set is always a trivial deformation over a point. There is no deformation at all. And saying this can be written in terms of equations. And then we use some Artin approximation theorem that will tells you that we can construct such Zariski equisingular deformation for which one of the fiber is a Nash set. A lot, in fact, but okay. That's for the idea of the proof. Okay. What is important here is that a Zariski equisingular deformation is not only a topological trivial deformation, but it has more properties. Just one remark also is that to transform a Nash set into an algebraic set, this can be done by a B-analytic map. So this step is we have strong regularity conditions. And the problem, the fact that we cannot find some C1 diffeomorphism, for instance, like in the Whitney example, comes from the fact that we cannot do it in the first step. So the homeomorphism constructed by a Whitney, Zariski deformation. So it's not only a homeomorphism, it has more properties. In particular, it's subanalytic. And it's also arcanalytic. So this result is due, it's a recent result due to Paruzinski and Paunescu. So subanalytic means that the graph of this homeomorphism is the projection, it's locally the projection of some analytic set. So it's not analytic, but it's piecewise the projection of some analytic set. So we have some kind of regularity property because a homeomorphism can be very wild in general. And arcanalytic means that the graph, still the graph of the homeomorphism, is analytic along real curves. It means that H, the homomorphism H, it means that for any curve phi, real curve into Kn, analytic, real analytic, H composed with phi is analytic. So H is not analytic in general, but long curves, it's analytic. So that's for question 1, but we can also answer question 2 in the same way. That's a result, recent result. It's a joint work we did with Adam Paruzinski and Marcin Bilski. That's essentially the same for functions. Is that question 2 has a positive answer. If H is chosen this homeomorphism. So the proof is based on the same ideas of Mostowski, but it's a bit more complicated because we need to deform the graph of the function f. It's more technical, but the ideas are more or less the same as the ideas of Mostowski. The difference here is that, yeah, I erase step 1 and step 2. In this case, step 2 is more complicated. We cannot transform easily a germ of a Nash function into a germ of an algebraic function. And in particular, we don't know if the homomorphism transforming a germ of function into a germ of analytic function into a germ of polynomial function can be chosen arc analytic and subanalytic. Because we know that it's true for homomorphism constructed from some Zariski deformation, which was step 1. But for step 2, here, we construct some homeomorphism, and we don't have any properties of this. And I will finish with some recent results. Is that, in fact, for both question 1 and question 2, we can do more than that, in the sense that, for instance, for question 1, we can transform V into an algebraic set defined over the rational numbers, the algebraic numbers, sorry. Like this, given V, analytic germ, there exists H, a germ of homeomorphism, such that H of V is a germ of algebraic set defined by polynomials with algebraic coefficients. So define with coefficient by polynomials in Q bar of x1, xn. And the same for question 2. Question 2 can transform an analytic series, an analytic function, into a germ of polynomial function with algebraic coefficient by such an homeomorphism. And there is an example of Tessier, which is a bit tricky, but that says that we cannot do more than that. We cannot transform even a germ of a polynomial function or an algebraic set into an algebraic set defined over the rational. Really need maybe algebraic.